Good evening, good morning, good night, everybody. It is my pleasure to open our seminar. Today we have Dr. Suvrat Raju from Bangalore. He will tell us about failure of split property in gravity and information paradox. Please, Suvrat, 1 hour approximately.
Okay, thank you very much to the organizers for inviting me to this wonderful set of talks. In fact, I've already seen some of these talks on YouTube and they've been really great. And I'm really happy we managed to figure out a time since we were discussing this from last semester to work this out. So I'm very glad that I'm with all of you today. Before I start my talk, let me just take a couple of minutes to acknowledge my collaborators. The work I'm going to speak about today started with this paper that we wrote with Alok, Siddharth, and Pushkal, now almost a couple of years ago, and another paper that has long been in progress and hopefully will appear this month. I've been incrementing this counter for some time, but hopefully it will converge soon. And then a follow-up with Chandramoli and Olga, and then another follow-up with Chandramoli, Olga, and Victor last year. And then 2 papers with what we call the group of 7, which is Hao, Andreas, Carlos, Lisa, Marcos, and Sanjeet, which appeared late in 2020 and last year. And also a couple of reviews that I wrote about this. So this talk will largely be based on this archive paper, which is in red, which appeared in October last year and has the same title as this talk. Okay, so let me just try and give you the theme of what I'm going to say. So the punchlines of what I'm going to talk about. So the theme of this talk is going to be that quantum information is localized very differently in gravity than it is in non-gravitational theories. This feature of gravity follows from rather general principles if one thinks carefully about the quantum mechanics of gravity. And this feature has important consequences for the black hole information paradox. And another consequence is that it explains why gravitational theories are holographic and why non-gravitational theories are not holographic. So that's another significance of this result. Okay, so these are the punchlines and these are the themes I'm going to try and persuade you of over the next hour. So let me start. This talk has a pretty simple structure. The first part is about the failure of the split property, which is another way of talking about the unusual localization of quantum information in quantum gravity. And the second part is about the implications for black holes. So that's the structure of my talk. So let me start by talking about the failure of the split property. So before I tell you about the failure, I should tell you what the split property is. So let me just remind you what that means. So the split property is a rather, it's a fancy name for a rather simple property that non-gravitational theories have. So in a non-gravitational theory, if one takes, imagine just a lattice theory of qubits, as we have here, then the state inside and outside a bounded region. So if you look at this pink region, it's a bounded region, and this is the outside. Everything here is happening at one instant of time. Right? I'm just trying to specify a state at an instant of time. So in a non-gravitational theory, this state can be specified independently in the pink region and in its complement. If you stare very carefully, you will see that here I have flipped this pin from being up to down, and I have flipped this pin from being up to down. But I could have done both of those operations or done neither or done one of them. And all of these are valid states in the theory. So it's, and this is a manifestation, it's a consequence of the fact that the Hilbert space factorizes in a lattice regularization of the theory. This property carries over also to the continuum theory. And the way it carries over in a non-gravitational theory is that we think of a region R, and we surround it with a small collar region, epsilon, just to regulate UV divergences. And then we call R bar, which is the complement of R union epsilon. And then the point is that if I give you a state and I tell you correlation functions on the region R for insertions in R, that does not in any way constrain correlation functions for correlators of insertions in R bar. In fact, you give me any 2 states, psi1 and psi2, I can find a split state that looks exactly like psi1 for insertions in R and looks exactly like psi2 for insertions in R bar. Okay, and that's the split property in quantum field theory. Now, the split property is actually very key. It's something, it's very key. We often assume it, we take it for granted, because it's very key to our idea about how information is localized. Right? The split property tells us, this is a cartoon, that we can prepare a state which looks exactly like the vacuum outside some bounded region, as you see here. And then it has some bump or some excitation inside this region. And what is more, we can change the form of this bump inside this region while keeping the form of this bump outside unchanged. Okay? So that tells us that if we have an observer who is here, that observer does not know what's happening inside this bounded region. The observer has to go visit that region. And the information about this excitation is available in this region, but it is not available outside, because outside this bounded region, the state looks exactly like the vacuum.
Oh,
so
excuse me, Raju, do you mean the region in space-time, or you mean the region in space only?
In space. So
okay.
Yes, in this entire discussion, I'm talking about discussions of how to specify states. So this is a Cauchy slice, and this is the spatial region. And in the spatial region, we have an excitation. Of course, if you wait, that's a good question, because if you wait for the passage of time, then this region will spread, and eventually the information will leak out. But here I'm just talking about the specification of states at a single time slice. Thank you for the question. Thank you for the question. Okay, great. Now I'm going to say that in quantum gravity, the split property fails. And in fact, quantum gravity obeys a very different property, which one might call the principle of holography of information. And this property tells us, the cartoon version, is that if you think of some bits or some qubits which are present in the bulk of a Cauchy slice, then this information about these bits is also available near the boundary of the slice, albeit in rather complicated form. But the same information can be read off in the theory of gravity from near the boundary of the slice. So, it's not that there's some other theory which knows about this information that lives on this boundary, but rather within gravity itself, there are some degrees of freedom here that know about what is happening here. Okay? Now, this is very different from the split property in non-gravitational theories. And let me just show you a cartoon to make that clear. You see, in a non-gravitational theory, I said that you could specify the state here and then change it in this region while keeping it unchanged over here. But what I'm saying in gravity is that, first of all, one cannot even specify a state of this kind. When we specify a state of this kind, one is forced to modify the wave function out to infinity. This is, in fact, also true in classical gravity. You put some excitation in some region, you have to have tails that go out to infinity. But there's a stronger statement, which is that if one changes the form of this excitation, then one is forced to change also the form of these tails. And there is I'll try and convey that there is a one-to-one correspondence between the form of this excitation and these tails out here. Okay, so you see, it's very different from the split property. Now, before I give you, yes.
So with split property, you always mean that basically you can write the Hilbert space like a tensor product of two sub Hilbert spaces.
Yeah, the split property is slightly more precise because, in a continuum field theory, the Hilbert space doesn't factorize, but that's a perfectly good way of thinking about it. If you just add some UV regulator, then that's precisely what it means.
And in the case of gravity, there is like a rigorous proof that this cannot be done, or is just some argument?
I will tell you the precise cases where one can prove that it cannot be done. So I'll give you some precise results as we go along. I'm going to give you an argument now why it can't happen in general, and I'll tell you the cases where we know the precise results.
Okay, thank you.
Okay, thank you. Okay, so great. So let me first start by giving you an argument for why it should be that this doesn't happen. And so thank you for the question, and I will then give you the precise results for when we know it cannot happen. Okay. Okay, so this is a natural question, right? Before I start giving you some results, you would like to understand why it is, from a physical point of view, that one should even believe that gravity localizes information differently. Okay, so let me just go back to something really basic. The moment we introduce quantum mechanics, we find we have an uncertainty principle, and if I give you something which has a fixed momentum, and in relativity, momentum goes with energy. So if I give you something which has a fixed energy, then in position space, the wave function is delocalized. Okay? Now, this is not usually an obstacle to localization, of course, right? We don't say this is an obstacle to localization. And the idea is pretty simple. In quantum mechanics, we simply take a wave function which is peaked at one energy, add to it a wave function peaked at another energy with the right phase, a third wave function with a third phase, and so on up to infinity. And if you do that, you can arrange for the entire wave function to interfere constructively inside some bounded region and interfere destructively outside that bounded region. So that is how we usually localize excitations in quantum mechanics. Okay, now what is different about gravity? So the key part that is different about gravity is something that's very basic, but as you will see has important implications in quantum mechanics. It is just the Gauss law. It is the fact that the energy can be measured out at infinity. In fact, the expression in a theory of general relativity, the expression at infinity is the only good definition of energy, and the expression you see in front of you is the expression for the ADM Hamiltonian. And that tells you that, if you have some energy sitting in the middle, there is some gravitational field out at infinity that is able to measure the energy. Okay, good. Now, how does that change anything about localization of information? You see, think back to this energy eigenstate that we were talking about, which was a delocalized wave function. Now, we understand that in a theory of gravity, in order to satisfy the constraints, in the full wave function of the theory, there must be also a gravitational field, a gravitational tail that lives out at infinity that is correlated with this energy eigenstate. Now you see that if you try to play the game that you played earlier, where you try to superpose a number of wave functions in a way so as to obtain constructive interference inside a region, destructive interference outside, you find an obstacle, and the obstruction is that every wave function that you had that had a given energy is now correlated with a specific degree of freedom at infinity, which takes on some value that is correlated with the energy. And this is really an independent degree of freedom. It's the metric out at infinity. And so because you have these tails that go out to infinity, while you might have arranged destructive interference for these matter degrees of freedom, these tails present an obstacle to having destructive interference outside a bounded region. And as a result, as I will emphasize, correlation functions of the energy and other observables carry information about the state. So it is not just the energy which carries information, but rather correlators of the energy and other observables at infinity carry information about the state. This is not a proof, but it is the physical intuition that you should keep in mind about why it is that gravity localizes information unusually.
Sorry, can I ask a question?
Yes.
So because you build up this intuition based on the Gauss law, right?
Yes.
And I wonder, why then the argument wouldn't be applicable in the case of EM, electromagnetic? Yeah.
Thank you. So you see, there's no uncertainty principle in the case of EM, right? I can just write down a local gauge invariant operator. There's nothing that says that if you have a given charge, your wave function has to be delocalized. Okay. Second, there's no positivity of energy. So these things are related. So I can take a positive and negative charge, I can put them together, I'll get a local gauge invariant operator. And what I'm talking about here is an obstruction to writing down such operators in gravity. But in the intuition that I gave, there is just no uncertainty principle that's associated with charge that tells you if you have a fixed charge, you have to delocalize the excitation, or if you have zero charge, that the excitation has to be delocalized. Whereas in gravity, if you think of an operator that has zero energy, it has to be a delocalized operator. That's the intuition. But there's a clear counterexample. You can just write trace of f squared in electromagnetism, and you can write e to the I trace of f squared. That's a unitary operator that that changes the state in some local region and doesn't change the state outside. And in fact, you can explicitly construct split states in electromagnetism and in gauge theories without gravity.
Thanks.
Okay, thank you.
Excuse me, can I ask a question?
Yes, of course. Yes.
Your splitting property refers to localization of quantum states in usual quantum field theory. But it seems there is no such notion like localized states in quantum field theory because of the Riesch-Schlieder theory.
Oh, no. So there is a notion of localized states even because of the Riesch-Schlieder theorem. The Riesch-Schlieder theorem says that the action of the algebra of operators in a bounded region can generate all states. But that doesn't mean that we cannot write down two states that look different inside a region and look identical outside that region. Two such states are just given by acting with unitary operators. So, the Rischlider theorem is not really saying that you can change something at infinity in a physical way. It's a statement about entanglement in the vacuum, and we will use it, in fact. So the action of a local algebra can generate all states, is dense in the full Hilbert space. But of course, there are commuting operators. So if I act with a local unitary operator in a region, there is no way an observer who's outside that region can know whether I have acted with the unitary operator or whether I have not acted with the unitary operator. So it's clear that in quantum field theory, we do have a notion of localization because there exist unitary operators that by microcausality commute with everything that is space-like separated.
Do you think that your splitting property is exact property or just for long distance?
No, the split property is an exact property. So the Rischlider theorem does not pose any obstacle to the split property. Remember that, I don't know if you're worried about the UV regulator, but so in this region, I was thinking of a region R and a region R bar, and there's a collar in the middle. And this is a property in axiomatic QFT, you would assume the split property would be one of the properties of the theory in quantum field theory. This is not in any kind of contradiction with the Rischlider theorem. This only says that you can prepare a state that if you look at correlation functions of the state in this region R bar and correlation functions in this region R, you can specify them independently. So there is a state psi, so that if you think of this set of insertions, for the set of insertions inside R, it looks like one state, and for the set of insertions inside R bar, it looks like the second state. This is an exact property of non-gravitational theories, non-gravitational quantum field theories.
Formula, the free scalar massive field, a two-point correlation function. Then you got zero from the right-hand side and non-zero from left-hand side.
No, the statement is not about correlation functions in the vacuum. The statement is I can find a state so that if I put an insertion, so for instance, let's say I look at a two-point function where I put an insertion here and insertion here. In the vacuum, there's a two-point correlation function, but I can also find a state where this correlation function just vanishes. So, I can find a state which breaks the entanglement between the two. And that's what the collar region helps you for. You can find, these split states are the analogs of product states. Imagine a product state, something that looked like psi1 in this region and psi2 in this other region. In this product state, there's no entanglement between the two, and the two-point function would also vanish. The vacuum is not a product state, but the split property is the statement that you can find states that look like product states, provided you introduce this epsilon region. So as was asked earlier, it is a statement about the factorization of the Hilbert space, and I will try and explain why that does not happen in gravity.
Thank you.
Okay, thank you. Okay, great. So now I'm going to give you some precise results. I will state the results without proof because of time, but I'm happy to go into proofs and arguments if there are in more details if there are questions. But let me just state what the known results are. Okay? So the first known result, which is where this can be made precise, is four-dimensional asymptotically flat spacetime. This is the Penrose diagram of asymptotically flat spacetime. And here we have Scri plus, and here we have Scri minus. Then the claim is that all information about massless particles, if you look at a theory of gravity which has massless matter, then all information about this massless excitations is present near the past boundary of future null infinity, which is this little red region here. Alternately, it is present near the future boundary of past null infinity, which is this orange region here. But everything I say about future null infinity has an analog for past null infinity. So I'll only make statements about future null infinity. And there's a similar statement for past null infinity, which I won't state separately. So let me just try and make this more precise and frame this in terms of the split property. So first, if we think of massless particles in flat space, these particles are conveniently described on Scri, either on Scri plus or on Scri minus. And the way it works is that both gravitational fields and massless matter fields have 1 over r tails at null infinity. So if one looks at the metric has some 1 over r tails which go by the name of the shear. This is the CAB, and this is called the Bondi mass aspect. And the derivative of this shear is what is sometimes called the Bondi news. If you have other massless fields, they also have 1 over r tails. And you can use this to define some fields which are intrinsic to Scri plus or to Scri minus in a theory in flat space. Now, in a non-gravitational theory, to specify a state, I can, one way to specify the state is to go to the out basis for the Hilbert space. In the out basis, to specify a state, I need to tell you correlators over all of null infinity. So if I parameterize null infinity or future null infinity with the retarded time that goes from minus infinity here to plus infinity at the tip of the cone, then to specify the state completely, I need to specify correlation functions of the state psi and these observables that I talked about in the previous slide, these tails, for all values of the retarded time. In this sense, future null infinity can be thought of as a Cauchy slice for massless particles. Okay? The result is that in a gravitational theory, it is sufficient to specify correlators on near the past boundary of future null infinity, which are correlators that are only in the retarded time from minus infinity to minus 1 over epsilon. This is a semi-infinite interval, but it looks like the small red region in this Penrose diagram. Okay? This is a non-perturbative result, which one can prove, and it makes some assumptions about the UV completion of low energy gravity, because of course we don't know the UV complete theory in 4-dimensional flat space. And the assumptions that it makes is that the Hamiltonian in the full theory remains positive, and moreover, that the vacuum of the theory can be identified by a boundary term in the full theory. So this is the precise place where we need the analog of the Gauss law. So if the Hamiltonian is a boundary term, then you can identify, of course, the vacuum. This is slightly weaker. It's the statement that the vacuum can be identified only by a boundary term. And a stronger version of this assumption would be that the Hamiltonian is a boundary term in the full theory. So this, it's surprising, but one can make a statement about the full theory provided we make these precise assumptions about the UV completion of low energy gravity, and one can also verify this perturbatively in the low energy theory. So you notice that this is a precise sense in which information is present near the boundary of the Cauchy slice, this red region, as opposed to being available all of the Cauchy slice. And this tells you that you cannot prepare split states in the theory, because if I tell you this set of correlators in this retarded time interval here, that completely specifies correlators on the entire slice. There is no more freedom that is left, which is completely the opposite of the split property.
Can this state psi be a vacuum?
Yes, the state psi can be the vacuum.
Okay, so can we go back to the slides, which is one of your first about splitting?
Yes.
Yes. So here you say this psi can be vacuum, right?
Yes. So this psi is a split state.
Suppose this psi are vacuum, right?
Yes.
So in quantum field theory, in the usual quantum field theory, this function is called Weitman function. Yes?
Yes.
Right.
Yes.
Okay. Now, if you have a quantum field theory and it is a consistent theory, there is only one vacuum, right? So this is vacuum. So this is vacuum. Psi 2 are also vacuum, right? Can
yes.
be. Okay. But this is not true in quantum field theory, because there is in quantum field theory, a factorization theorem of Weitman function when the x and y, all of them are compared to each other in outside of light cone. So this is true, but not everywhere. So
this is not true. This is a Cauchy slice. So everything is these are all correlators on a single Cauchy slice. That's point one. Second, your question is a good one. Let's say we had the vacuum. How would I? Why is it that in the vacuum there is no
psi to be a vacuum? This psi, and of course in quantum field, you say in any quantum field theory non-gravitational, right? So this psi is vacuum because vacuum is unique. So psi 1 is also vacuum, psi 2 is also vacuum, and this is not valid in general. Only it is valued. This is a well-known theorem of factorization for Weitman functions.
Sorry, I'm not sure I understand the question. Psi is the state that we need to find. Psi 1 and psi 2 here are states you can specify. So in a quantum field theory, you could specify psi 2 to be the vacuum, and you could specify psi 1 to be whatever you like. And then I would find for you a state psi. So it says you specify state psi 1 and psi 2. And I would find for you a state psi, which would look exactly like the vacuum in this outside this region. And it would look like whatever you like inside this bounded region. So this is just a standard property of quantum field theories. I think this is, you're right, and functions, they're all...
This I don't understand. This I don't understand.
So,
because
so let's say psi2 is a vacuum. Notice that I have specified. So this is just a property of quantum field theory. Here, I'm not in this slide. I'm not saying anything.
You agree that if you put here this psi, this is Weizmann function, right? This is Weizmann function.
These are all Weizmann functions. They're all in a single Cauchy slide.
So psi is vacuum, then this psi1 and psi2 have to be also vacuum, because there is a uniqueness of vacuum in quantum.
But that is not, if psi is never the vacuum is never a split state. The split state is
psi, I'm speaking psi and psi1, psi2, they are vacuum states, right?
Then this equation would not be true, because in the vacuum state, you would have cross correlations between correlators. Just think of a 2-point function, psi of x1, psi of x2 in the vacuum. This equation would not be true. So the vacuum is never like a split state, because it has long range correlations between a point here and a point everywhere else. So we never take psi to be the vacuum. The claim is you specify psi1 and psi2, and I will find for you a split state psi. The vacuum is never a split state because it has arbitrarily long range correlations.
But you said that this psi can be a vacuum, you said, right?
No. I said the psi in the previous slide can be at the vacuum. This psi here is different. I said that the psi that I had in the correlator in the previous slide was the vacuum. In this setup, psi is a split state, which I will find for you if you tell me what psi2 and psi1 are. So you tell me what state you like for this region outside. You tell me what state you like for the region inside. I will find for you a third state psi, which will look like psi2 in the region outside and will look like psi1 in the region inside.
Okay,
that state
so
will never be the vacuum.
This is not a proof. All right, we can go.
This is not a proof. This is a very standard property of quantum field theories. Just imagine you have a product state. So let me just write here. So imagine you have a lattice factorization. Then this state psi is just the following state, right? You just take like trace of psi1 over the region R bar, and cross it with trace of psi2 over partial trace over the region R. So the fact that the Hilbert space factorizes in a lattice regularization tells you can do this. I mean, I can go back one more slide, but this is simply the precise version that the Hilbert space factorizes.
Exactly what I say. This is true when the xi, all these x and two y's are mutually outside of the right cone.
They're all, because they're all in a single time slide.
Because of causality. Okay, so this is a point, of course, I see that we cannot agree, but probably one has to think of it. Anyhow, you can.
Okay, continue. I'm not sure. These are all in a single time slice. So there is nothing here everything is outside everything's light cone, because this is, as was asked in the beginning, this is on a t equal to 0 slice. So this is, okay. Maybe
right. So we can maybe continue later. Thank you.
Yeah, thank you. Yeah. Okay. So just to go back, maybe I can take this opportunity to explain one thing though. In this question you could have asked, why can't I find a split state in gravity for the vacuum? So I'll go back to my other slide. Let's say I said that psi2 was the vacuum, right? And I said, find for me a state which looked like the vacuum in the region R bar and looked like some excited state in the region R. The point is, one of the operators in the theory is the Hamiltonian. And by measuring the Hamiltonian in the state psi2, you know that the Hamiltonian is 0. And if you know that the Hamiltonian is 0, that removes any freedom that you have to specify the state in the region R. In fact, this is not exactly correct in 4-dimensional asymptotically flat spacetimes, because the vacuum is not unique, and that's a complication that we need to deal with because there are these supertranslation, there are these vacua which are labeled by supertranslation charges. But you can see that had the vacuum been unique, then merely the fact that the Hamiltonian is an operator in R bar would be sufficient to completely specify correlators in psi1. So once I specify correlators in psi2 in a theory of gravity, and I'd say that psi2 is the vacuum, you would see there's no more freedom here. Of course, this does not prove the general result, but the general result in 4-dimensional asymptotically flat spacetimes is the fact that for a state of massless particles, specifying the state in this range of retarded time is sufficient to specify the state everywhere. Let me say a few words about massive particles. This is work in progress. We would like to propose that massive particles can be understood on the blow-up of spatial infinity. So what I was speaking earlier was about the retarded near the past boundary of future null infinity. The blow-up of spatial infinity is a construction that's used by relativists where, and one way to understand it is to just think of Minkowski space in these coordinates where rho is a light cone distance. And then we take the limit rho goes to infinity. So in the conventional Penrose diagram, spatial infinity is just a point, but this blows up that point. It gives you a resolution of that point and gives you a copy of three-dimensional de Sitter space instead of just a point, which interpolates between past null infinity and future null infinity. And one can check that massive fields have an exponential fall off as one approaches spatial infinity. And the claim is one should keep track of these exponential tails on spatial infinity. And then the result is that if one specifies correlators on all of future null infinity and on a band of this spatial infinity. So this is my cartoon of spatial infinity, and this green region that you have to squint to see is the band on spatial infinity, that these correlators are sufficient to specify the full state of the theory. So this is the precise sense in which, if you think of a Cauchy slice, this region at spatial infinity and the union of this region in null infinity, which you can think of as the regions on the boundary of the Cauchy slice, are sufficient to specify the full state in the theory. Okay, one can make a similar argument in ADS, and let me just state what the result is. The argument is that asymptotic correlators on an infinitesimal time band on the ADS boundary, so this is ADS, it looks like a solid cylinder, and the claim is these correlators are sufficient to completely fix the bulk state. Now, I want to emphasize that from the point of view of ADS CFT, this is an obvious result. I mean, it's in fact, we need asymptotic correlators on a time slice, not on a time band. But the result I'm describing now does not assume ADS CFT. Rather, it provides an argument for why gravitational theories are holographic, and it is subject to the same assumptions that I described previously, which is that the Hamiltonian is positive and is given by a boundary term in the full theory. And if this is true, one can argue starting from gravity that asymptotic correlators on this band are enough to fix everything in the bulk, which of course would not be true without gravity, because you would need then asymptotic correlators on the entire boundary of ADS. So this is allowing you to squeeze this entire boundary of ADS into a small time band on the asymptotic boundary. Okay, now let me ask the following question, which perhaps some of you have in mind. I'm giving you various arguments. In fact, I haven't even given you proofs, although, as I said, I'm very happy to give more details of the proof. But, you might say, fine, there's something being said, but I don't believe it. What is it that's going to prevent me from just writing down two wave functionals of this form below? I'll write down one state, which has an excitation. It looks like the vacuum. I'll write down another state, which has a different excitation and looks like the vacuum. So, we have a Schrodinger representation of states in gravity, and I'll just write them down. Whatever argument you're giving must be wrong in some sense. Right? So now the point is that in the quantum theory, and another way to understand what I've been saying is that not all wave functionals are allowed. And in fact, the set of allowed wave functionals must obey some constraints which go by the name of the Hamiltonian constraint and the momentum constraint, which simply represent the diffeomorphism invariance of the theory. The Hamiltonian constraint is also called the Wheeler-DeWitt equation. And so the main point is that not all wave functionals are allowed. So one can't just write down whatever wave functional one likes. One has to make sure it satisfies the constraints. If one analyzes explicit solutions to the Wheeler-DeWitt equation in perturbation theory in anti-de Sitter space, so we don't know how to do this in flat space yet, but in anti-de Sitter space in perturbation theory, one can prove that two solutions of the Wheeler-DeWitt equation that coincide at the boundary for an infinitesimal amount of time must coincide everywhere in the bulk. This is the same result that I showed you previously, but it's a weaker result because it's a result that holds in perturbative quantum gravity. But it's a very explicit result in that if you look at our paper, we have explicit solutions, and this is not a result that requires any assumptions about the unknown UV completion of gravity, but one can just show directly starting in the low energy theory and looking at solutions of the Wheeler-DeWitt equation that this property must hold. And in this sense, information must be available here, because if once I tell you the wave functional on this time band, that tells you the wave functional everywhere or for all times. Okay, let me try and give you a few arguments about how this goes, just a few details. The main point is, just because it makes contact with some of the physical intuition, the main point is that, we look at a particular solution of a particular linear combination of the Hamiltonian constraints. So the Wheeler-DeWitt equation is called equation as if it's singular. In fact, it's an infinite number of equations because it's an equation at every point. And we look at a particular integrated version of this Hamiltonian constraint. And we are able to show that if one looks for solutions of this integrated version of the Hamiltonian constraint, then these solutions take the form of some matter wave functional in a Fock space, because we are working in the perturbative approximation, entangled with a particular degree of freedom of the metric. So this HTT is some degree of freedom in the metric, this is some other matter field, and this is another degree of freedom in the metric. The notation is not important, but what is important is this realizes precisely the cartoon that I showed you at the beginning, where I said, there was a wave function and it had to be correlated with some degrees of freedom at infinity in order to satisfy the constraints. This is a precise version of that, and we can explicitly construct these solutions. And then one can show in this space of solutions that if one looks at some arbitrary mixed state in the space of solutions and imposes the equality of the following boundary correlators. This H delta is an integral of the metric that's like the ADM Hamiltonian. And these O's are other insertions of fields at the asymptotic boundary in this asymptotic time band from 0 to epsilon. So one can show if one imposes the equality of these correlators, which I emphasize are correlators of the energy and of other observables, this is sufficient to completely fix the state, in that if two states have equal correlators of these insertions, they must be equal. So it is in this sense that correlators of the energy and other degrees of freedom completely specify the state in the bulk. Okay. So I will now speak about the implications of these for black holes. As I said, I'm happy to give more details of these arguments, or there are any questions, I'm happy to take them now. Yeah.
If I can ask a question,
yes.
So I would like to understand better the physics of this failure of the splitting property for gravity.
Yes.
So does this mean that, like in general gravity, at least in general relativity, so gravitation interaction described by general relativity is intrinsically non-local?
Good. Yeah. So locality is a more subtle question than the failure of the split property for the following reason. When one asks a question about locality, one assumes that there is a notion of split states. So how do we ask the question? We say we have two states, they differ inside a bounded region and they coincide outside. And then we look at how fast the boundary of that differing region expands. That allows us to ask a question about locality. In gravity, the claim is that the information is always outside. So it is not, one shouldn't think of it in terms of non-locality, in that if one does something at infinity, the information will be inside, but rather that, that the information is always outside. So it's not that if I do an experiment here, the information propagates outside at faster than the speed of light, but rather that the state is such that the information that I'm going to gain in the experiment and the information that I am going to do the experiment is already present at infinity. So it's a slightly more subtle issue. It's not that there is a non-locality in the sense of superluminal propagation. There's no violation of superluminality. It is the fact that the information is always available outside.
So basically, for instance, if you take two fields, one field in one region and the other in the inside region, for instance, outer and inner region, you take the commutator of these fields in curved space for space-like separation, you still get zero?
No, you won't get zero, but you see the reason you won't get zero is because the fields, there is no such thing as a local gauge invariant operator. So when you try to write down a gauge invariant version of the field, you will have to dress it by means of a Wilson line out to infinity. And then, there is some operator outside with which this field inside won't commute. So it is true that you won't get zero, but the fact that you won't get zero is also because you will not be able to define exactly a local gauge invariant operator. So if you could define local gauge invariant operators which are space-like separated, they would commute. One example of when you can do this is if you take two regions, both of which extend out to asymptotic infinity. So I take the left half of the space and the right half of the space. Then I can dress operators in the right half to the right side and operators in the left half to the left side. Those operators would commute if I did that dressing. But the geometry I'm speaking about here is where you have a bounded region. and you have the complement which surrounds the bounded region. But operators in a bounded region, the moment you dress them, you have to run a gravitational Wilson line which has to cross the complement. And therefore, there is no way to write an operator in a bounded region that commutes with everything in the complement. But that is, that operator is non-local to start with. So it is not that there is some gauge invariant operator which fails to commute at space-like separation. It is rather that there are no local gauge invariant operators, so there's no contradiction in that sense. Does that answer the question?
Yeah, I think so. But so basically, the fact that this commutator relation is not zero for space-like separation is not like in one-to-one correspondence with this failure of the splitting symmetry.
It is closely related that the commutator is not zero at space-like separation. I'm just saying that space-like separation is tricky to define because these operators that you thought were space-like separated were actually non-local operators. So you thought you had a field operator inside a region and a field operator outside, and they were space-like separated. But when you try to make them gauge invariant, the field operator inside you have to dress with a Wilson line, and it's that Wilson line that fails to commute with something outside.
Okay.
So in electromagnetism or a gauge theory, I would have just written down trace of F squared. I would have taken a positive and negative charge, and I would have made a local gauge invariant operator, or I would have taken a Wilson loop and made it gauge invariant. But there is no such way to write down a local gauge invariant operator in gravity. Because to make it zero charge, it has to have zero energy, and therefore, by the uncertainty principle, it has to be delocalized.
So just one last question.
Sure.
So is it correct to say that, for instance, in gauge theory, non-gravitational gauge theory, like the splitting property does not fail because I can still write like a local gauge invariant operator?
Exactly. It does not fail because of that. In fact, it's exactly the same in the form I stated in a gauge theory. In a gauge theory, there is some issue about factorization of the Hilbert space because the algebra of local regions has these centers. But the moment you introduce this Collar region, that I introduced in the first slide, it holds in exactly the same way. And that is because if I have a Collar region, I cannot, from outside that region, even tell what is the charge in the room. If I have this room and I introduce a collar around the room, even if I put some positive charge here, I can put an arbitrary amount of negative charge in the collar around the room. So that once you go out to infinity, you cannot even tell if I have the total charge inside the room. And exactly as you said, the simple fact is that there are local gauge invariant operators. And so there is, in a non-gravitational gauge theory, the split property holds exactly as it does in other theories.
Like maybe in this sense, you could kind of quantify the failure of the splitting with this commutator. Like for instance, I don't know.
So the failure of the splitting is related to the commutator. So in perturbation theory, for instance, Giddings and Donnelly have computed this, but it's more the failure to be able to dress in a local way. You could take non-local operators in gauge theories and they would also commute, but the answer is just that information is localized because you can always dress in a local way. You never have to dress out to infinity. In gravity, you always have to dress out to infinity because of the uncertainty principle. So there's something physical happening there. Zero energy corresponds to delocalized operators.
Okay.
Could one say that the difference between a non-local quantum field theory, where this factorization or splitting does not occur, and gravitational theory is the following, that in a non-quantum field theory or non-computative theory, all the boundaries have to be put by hand, while in gravitational theory, the boundaries come out from the theory. Can one say such a thing?
I'm not sure that is related.
Horizon, can one say this is the...
I'm not sure that is related. And especially the notion of a horizon is not so relevant here because a horizon is something which is a property of the space-time, whereas the failure of the split property is something which holds on a Cauchy slice. So as I'll discuss for black holes now, the horizon is not relevant because we are just speaking of a single Cauchy slice. So I'm not trying to say something about how something evolves in space-time. Maybe we can discuss it later again, but I think it's not a somewhat different statements.
Yes.
Hi, Suvrat, just a quick question.
Yeah.
Till now, whatever you have discussed, the black holes are not in the picture because you have shown one kind of a Penrose diagram where you say that near I naught, some information is stored. So that is purely an asymptotically flat space-time, no black hole.
Thank you. Black holes are in the picture because for me, in asymptotically, I think of black holes that always evaporate. So I don't have the perspective that relativists have where the black holes have a different Penrose diagram. For me, in asymptotically flat space, black holes always evaporate. So the Penrose diagram in terms of the structure of asymptotic infinity is always the same, whether or not there was a black hole in the bulk. So if you prepare an in-state, it prepared something, but eventually it evaporated. So for me, the Penrose diagram does not change in the presence of a black hole, because black holes are never really eternal for me in flat space.
But the Cauchy surface will change in the presence of a black hole.
Why will the Cauchy surface? I mean, the result I showed right now was a result at asymptotic null infinity, right? So null infinity is null infinity, whether there was a black hole somewhere in the bulk. I'm saying words about
null infinity will not be a Cauchy surface. You have to add the horizon also, right?
That's what I was saying. So I was, this is true in classical general relativity. But you see, if the black hole always evaporates, then it doesn't change asymptotic infinity in any way, right? If the black hole is some intermediate state that forms and evaporates away, then null infinity is still a Cauchy slice. Right? You see, because the black hole.
Your picture had the horizon or only the null infinities?
No, my picture had only null infinity, but that is enough even for black holes, because black holes always evaporate. What you're saying about the horizon is a statement about classical GR. In the classical Penrose diagram, you're right that, if I look at the future slice, I have to take the union of H plus and Scri plus. But notice that if the horizon, if the black hole evaporates, then once again, all the information comes out at null infinity, right?
Yeah, but were there any statements regarding the holographic relation between the information loss and storage of information at infinity?
I will make some statements now for black holes, but I just want what the question you asked is an important one, but I want to emphasize that the structure of asymptotic infinity is not changed in the presence of black holes if black holes always evaporate.
Yeah. Okay.
Okay. Thank you. Okay, great. So now let me go on to black holes, since there were questions. It'll take me about 20 minutes more or 10, 15 minutes more. I hope that is okay, since there were many questions to the organizers. Can I do that? Or?
It is okay. It is okay, no problem.
Okay, thank you. Great. Okay, great. So yes, please. Fine. So the holography of information, here's the cartoon version. What does it say about black holes, right? So as I said, the results I was giving previously apply in the presence of black holes. And the holography of information in the cartoon version says that information about the microstate is always available outside with the right measurements. And this is, for related perspectives, this is something that's been explored by several authors. So these are related perspectives. Okay, now let me make a slightly more precise statement. Okay, so here is a Penrose diagram of an evaporating black hole. As I said, in classical general relativity, you would just think of the horizon, but if the black hole evaporates, all the information eventually comes out to Scri plus. The statement is that the von Neumann entropy of a segment from -infinity to u of Scri plus is independent of this upper limit u. And you see, this is not, one can show the statement using the same arguments that I alluded to previously, but this is not surprising, because if if the set of operators here has full information about the state, then it is clear that by going further, you get no further information about the state. And for this reason, this von Neumann entropy is a constant. So in this sense, information is not lost, and neither is it gained as we go forward on future null infinity. Okay, so this is a precise statement about the fact that information is not gained or lost as we go forward in terms of the entanglement entropy of this region. Okay, now let me say what this means about the Hawking paradox. So of course, this contradicts Hawking's suggestion that the entropy should rise monotonically. So Hawking also had a curve for the entanglement entropy as a function of the retarded time, and Hawking's suggestion was this is something that should keep going up and up. So what is the difference between the calculation that I'm presenting and and Hawking's proposal for what this entropy should be? And this is an important question, because one might say, you're saying the entropy is a constant, but Hawking says the entropy should increase. So what is the error in Hawking's argument? Why do you get a different answer than this answer that Hawking had? Okay. So what is the error in Hawking's argument? Okay, so let me first make a clarification. I think this is sometimes overlooked. What Hawking computed. So Hawking had two parts to his. There were two papers he wrote on this issue, or many papers, but two famous papers. And one of them computed some Hawking radiation. And in that computation, Hawking found that if one looks at the occupancy of modes at future null infinity, photons or gravitons, that occupancy is thermal. And this is a completely correct computation. There is no error in this computation. It would be, we have not observed it, but it would be staggering if we were not find this for a black hole when we could observe this. Okay? But this computation is not enough to lead to a paradox. And I want to emphasize this. That is because pure states are exponentially close to mixed states. So if I just tell you that the occupancy of some modes is thermal in a leading order computation, unless I can control the e to the minus s/2 corrections, that is not enough to lead to the conclusion that the state itself is mixed. It could well be that the state is pure and this result could still hold. So low point correlators cannot be used to conclude that the final state is mixed. And this was not Hawking's argument. So one should not think, I think it's a common confusion that the argument is sometimes said in the words where one says Hawking computed the radiation, found it was thermal, and then argued there was a paradox. But this is incorrect, because even at that time, it was understood that this computation is not enough to lead to a paradox because of this very robust property of statistical mechanics, which is that exponentially small corrections can unitarize a seemingly thermal spectrum. Okay. So what was Hawking's argument? Hawking's argument was the following, and he's very clear about this in his paper. And his argument, he gave an argument to suggest that the conclusion was robust against small corrections. His argument was not just I did the computation and found the spectrum was thermal. And Hawking's argument was what he called the principle of ignorance. And this is what he says about the principle of ignorance. This is really a screenshot from Hawking's paper. Hawking said one has to introduce a hidden surface about every black hole and apply the principle of ignorance to state that all field configurations on the hidden surface are equally probable provided they are compatible with the conservation of mass and angular momentum and other charges which can be measured at infinity. But notice this is a statement about the classical no-hair theorem. It is a statement that if you think about a black hole, there is a causal structure of the black hole space-time that one should take very seriously, and information inside is unavailable to the observer outside except for conserved charges. So this is the statement that the Hilbert space does factorize up to a few global constraints. But what I've been trying to say is that this is manifestly false if one thinks carefully about the structure of the wave function in gravity. In fact, Hawking went on to say, let H1 be the Hilbert space of data on the initial surface, by which he meant scry minus. Let H2 be the space of data on the hidden surface, which is the part of the surface inside the horizon. And H3 be the data on the final surface, by which he means scry plus. Then he says the basic assumption of quantum theory is that the Hilbert space factorizes. And then, that you trace over the hidden surface. That is what he calls the principle of ignorance, because that is unavailable to the asymptotic observer. And therefore, you get a mixed state for the asymptotic observer. But you see, this factorization is an assumption of the split property. It is an assumption that if you take a nice slice through the black hole geometry, you can specify data independently on the hidden surface that is lost to the asymptotic observer. So if somebody asks, where is the error in Hawking's argument? It is here in this paragraph. One can point to this paragraph and say it is here that there is an error in Hawking's argument. And it is for this reason that one obtains an answer which is different by thinking carefully about how information is localized in quantum gravity than what Hawking found. And this is where there was an erroneous argument made. Now, because the split property is so natural, this property has arisen again and again and has repeatedly led to paradoxes. One such set of paradoxes was discussed intensely, about 10 years ago, starting with the work of Mathur and then the EMPS firewall. And their argument was similar. If one takes a nice slice through the black hole spacetime and one divides it into three parts, A being outside, C being far away, B being inside, then one can argue on general grounds that there will be a violation of the strong subadditivity of von Neumann entropy. But the framework of this entire argument assumes factorization. Strong subadditivity assumes that the Hilbert space on the nice slice factorizes into HA times HB times HC, which is the same assumption that Hawking made, which is the assumption of the split property, or a slightly looser way of assuming the split property, which is false, and it's demonstrably false in a theory of gravity. So once again, the resolution to this paradox is that the Hilbert space does not factorize. And in fact, the degrees of freedom inside are also available outside. Okay, now let me now turn to more recent work, and let me point out that this curve that I'm showing is also different from the conventional page curve that's often drawn, which is, a tent-shaped curve. And why is this different? Why is the curve I'm showing for the von Neumann entropy does not even obey the page curve, where Page said information emerges gradually, whereas the result I showed suggests that in the theory of gravity, the information is always available outside. And the reason is that Page also assumed factorization. In fact, if one looks at the argument that Page had right in the beginning, Page speaks of two subsystems, one of dimension m, the other of dimension n. They come together as a big system, and then Page talks about the entanglement entropy of a subsystem. This is a nice calculation. It's valid for non-gravitational systems. It's completely valid. It's correct for non-gravitational systems, but it's true only when the Hilbert space factorizes. In fact, in applying this computation to the black hole, Page assumed that the black hole is a subsystem which has dimension m. The radiation is a subsystem which has dimension m, and these subsystems together form a total system in the pure state and of dimension mn. But since the Hilbert space does not factorize in this manner, we should not expect the entropy at Scri plus to follow a Page curve. So if one were to ask, why does the result I'm presenting for the entanglement entropy differ from the Page result? It is for this reason that the Page argument also assumes factorization very explicitly in the argument, which is false in a theory of gravity. Okay, let me now say some things about, and that answer a question before it is asked. We live in a world where gravity is presumably quantized, but we do expect that for ordinary systems like coal, we will see a Page curve, right? We expect that we can treat them in the non-gravitational approximation. We expect we can treat systems like coals as subsystems, where we see a Page curve. And the question is, why am I saying that we do see a Page curve for coal, but what is so different about black holes, right? Presumably gravity is quantized. So why do I say sometimes we see a Page curve and for black holes we don't? It has to do with how the parameters scale, and this is an interesting thing to keep track of. You see, to see a Page curve, it is important that we keep track of effects of size e to the minus s, where s is the degeneracy of microstates of the system. That's just because, as I said, pure states and mixed states differ at this exponential order. And so unless one keeps track of these effects, one makes measurements which are accurate to this order, one cannot see a Page curve, right? Now, for ordinary systems, the effects that I have been speaking about are all gravitational effects, and they're controlled by this parameter, which is g Newton times the energy scale of the system to the power d minus 2. So, now in ordinary systems, we can always work in an approximation where we ignore this parameter, but we keep the degeneracy of microstates finite. So there is an obvious protocol for coarse graining observables where we keep track of observables to this accuracy, but we ignore all the effects I'm speaking of. And then in that approximation, we do expect to see a Page curve for ordinary systems, which is, we can ignore all these unusual effects of gravity that I'm speaking of. On the other hand, notice that in the case of black holes, if you take E to be the energy of Hawking quanta, which is the natural energy scale in the system, then these effects are 1 over the entropy of the black hole. So there is no sense in which we can keep track of effects which are suppressed by e to the minus s, but forget about the unusual localization of information in gravity for black holes. So for black holes, there are no separate parameters that control whether you see, whether you can see purity and whether you can see these unusual localization of information in gravity. Okay? So just to make it clear, even for black holes, one can look at just coarse-grained observables, which are few-point correlators of light fields. And, then you would see the thermodynamic entropy. You would see the Bekenstein-Hawking entropy. One can look at fully fine-grained observables, which is the set of all asymptotic correlators. In this approximation, one would see all information at all times. Now, perhaps there is a set of intermediate observables, and I can give you some plausible guesses for what those are, which are in the middle of these two, where one sees the Page curve. So one first loses information and then regains information, although it's not clear why these observables are of intrinsic interest, but it's quite likely one can construct such observables. But in these two natural limits, this is what one sees. Okay, now let me just spend the last 5 minutes to explain the relationship of or everything I've been saying to recent computations of the page curve. So of course, as you're all aware, there have been a lot of recent activity in the HEP-TH literature on computing the page curve for ADS black holes. Now, the first thing to say is that these computations do not contradict anything I'm saying so far. And the reason is that they all involve non-standard models of gravity. Although this is not always emphasized, it's an important fact, and I'll explain how these models are non-standard. These models that are used to compute the page curve are non-standard in two ways. First, gravity is not dynamical throughout space. So one thinks of an ADS bath and one couples it to a non-gravitational bath. So gravity switches off at some point. Second, in the region where gravity is dynamical, at least for dimension larger than 2, and I'm restricting all my comments to dimension larger than 2, the graviton has a mass. And so there is no Gauss law in these models, and therefore no holography of information either. So let me just explain these points in turn. So first, this point about the non-gravitational bath. So if one looks at this setup, then one sees that, the way to understand this ADS black hole coupled to a bath, the most precise way to think of this is in terms of what's called a BCFT, which is a CFT on a space with boundary, where you just replace this entire gravitational region with a defect. And then the computation that is carried out in some precise way in these models is you compute information transfer across an interface on the non-gravitational bath, so across this dashed line. But of course, on the right-hand side, the entire description is non-gravitational. Therefore, the Hilbert space factorizes, there is a split property, and there is a page curve as one would expect. On the other hand, if one even turns on weak gravity in the bath, and this was our paper with the first paper with the group of 7, then one can show this page curve vanishes in a model if one turns on weak gravity. So these calculations that are performed are genuinely non-gravitational. They are really computing information transfer between two non-gravitating parts of the system. And so these calculations are correct, but I think it's somewhat imprecise to term this the page curve of Hawking radiation. It is the page curve of two parts of a bath that one can compute in a very nice way using very elegant techniques. But it's not the page curve of what I would call Hawking radiation. Second, there's another aspect to these computations. These page curve computations involve the so-called island proposal. And if one thinks a little carefully, this island proposal suggests a factorization of the bulk Hilbert space where gravity is dynamical. That's because this pink region, which is my cartoon of the island, is believed to be in these models dual to some region of the bath. And the complement of the pink region, this white region, is dual to some other part of the bath. And this would suggest, since the bath Hilbert space factorizes, that the gravitational Hilbert space factorizes. But in fact, these models would not work, or this island proposal cannot be consistent in a theory where the Gauss law applies. And this is not just because the proposal is inconsistent with holography of information, as I was presenting previously, but one can see this inconsistency within perturbation theory. Now, in perturbation theory, if the Hilbert space factorizes, I should be able to act with a unitary operator inside the island in such a way so as to leave operators outside unchanged. And one can show that if the Gauss law applies, and if I try to act with a unitary operator inside the island, then one finds that one changes the value of 2-point functions outside the island. So in a theory with long-range gravity of the kind that exists in our world, one would not expect the island to exist, or one would not expect an island to exist of this form, which has a non-trivial complement. This is not, again, in contradiction with any of the computations that have been performed, and that is because all these computations have been performed in a theory where in the region where gravity is dynamical, the graviton is massive. Let me tell you the quickest way to see why the graviton is massive. If one thinks of first the ADS theory of gravity before you couple it to a bath, the left side of this picture, there is a stress tensor on the boundary of ADS, which is conserved. And the stress tensor on the boundary of ADS is conserved in ADS CFT. Once one couples it to a bath, one finds that the stress tensor is not conserved by construction because we want energy to flow into the bath. But in conformal representation theory, the conservation of the stress tensor is the statement that the stress tensor lives in a short representation of the algebra. The non-conservation is the statement that it has picked up an anomalous dimension. The fact that the stress tensor has picked up an anomalous dimension therefore corresponds to the fact that the bulk ADS graviton has picked up a mass. And this argument was first made by Aroni, Clark, and Koch many years ago. So in these setups with a non-gravitational bath, the bulk graviton has picked up a mass. And one can show in such massive theories, islands make perfect sense, because in massive theories, the Hamiltonian is not a boundary term. In fact, the best way, or one good way to realize massive gravity is by means of these so-called Karch-Randall brane worlds, which are now called doubly holographic models, where one thinks of a brane, ADS brane in ADS space. And this ADS brane, this larger theory in a higher dimensional ADS space has an effective description as a theory of gravity coupled to a bath. But in the theory of gravity, it's clear the Hamiltonian is not a boundary term that's given at this point, at the boundary of the brane. Rather, the Hamiltonian is an integral over this entire boundary. And the island rule reduces to the usual Ryu-Takenagi prescription in these doubly holographic models. And it's explicitly consistent because you see in this setup, this island or operators in the island can be dressed to the bath through this extra dimension. Another way of saying this is as follows. If one looks at the constraints that the gravitational theory must obey on the brane, they take the form of the divergence of some current is equal to the density, energy density on the brane. And then there is this additional term which corresponds to the mass of the graviton on the brane. If this term had not been there, you would have integrated both sides and you would have found that the Hamiltonian was just a boundary term and that the integral of rho was a boundary term. But in the presence of the mass, you see the left-hand side is not a total divergence. And this mass, in fact, does correspond to the fact that one way to think of this theory is by means of this extra dimension, and the constraints can be satisfied by dressing excitations in this extra dimension. But the key point is that the Hamiltonian is not a boundary term in these theories because the graviton is massive. So there is no Gauss law. And so in these theories, islands make perfect sense. Okay, so I'm done. Let me just summarize and then I'll stop. I'm a little over time. So the point of this talk was that standard theories of gravity store quantum information very differently from local quantum field theories. This is a principle that we call the principle of holography of information. It's a result one can prove non-perturbatively without knowing the full UV theory of gravity, provided one makes some weak and specific assumptions about the UV theory. On the other hand, for simple states, this result can be verified in perturbation theory, and we think that adds to the result, the fact that perturbatively one can check that these results are correct. I think this sheds light on why gravitational theories are holographic and non-gravitational theories are not, and that's one reason I think this result should be of interest. Accounting for this unusual localization of information helps to resolve several paradoxes about black holes. Conversely, forgetting about this property of gravity, and if one assumes that the Hilbert space must factorize because that's what we assume in non-gravitational theories, that's often a recipe that leads to a paradox. The idea that the entropy of Hawking radiation obeys a Page curve also involves an assumption of factorization. So we think a better way to think about this entropy is that it is a constant in that information is always available outside. This is not in contradiction with recent computations of the Page curve, but that is because these computations are performed in non-standard theories of gravity, which involve a massive graviton and a non-gravitational bath. In such theories, the Hilbert space does factorize. And so the Page curve is the correct answer in such theories, but perhaps not in a realistic theory of gravity. Okay, I'll stop here. Thank you for your patience and apologies for going a little over time.
Okay, thank you very much for your very interesting talk.
Thank you very
Questions,
much.
please. Please raise your hands to ask your questions. Who is first? Sravan, please.
Hi, Suvrat. Thanks for the very nice talk. Well, you spoke about black holes, but my question is a bit different. So as you said, the main point is Bliss property does not hold in gravity. So what is the implication of this for inflationary correlations, and can we test it?
Good. So we don't understand how this works in de Sitter. That's a great question. And we would like to understand that, but we do not have a good understanding of that. It's a very interesting question. We would like to know the answer, but we don't know the answer.
Okay.
So I don't have a good answer to give. It's a great question. I can only say it's a very good question. And I would like to know the answer too. I think there should be an answer, but I think it should be probably a very interesting answer, but I don't know what it is.
Because that's the only place where we know, where we quantize and see implications of this in the CMB or primordial gravitational waves. I think that's the best place. But I have a follow-up question, because you said it is de Sitter case and it is there's no answer. Then, because in the end, toward the end of the talk, your conclusion was that at least the recent Thailand proposal and all, they are consistent because they assumed ADS space, which give like graviton mass. But
they're inconsistent because they have a non-gravitational path. In these proposals, gravity switches off abruptly. So it's a universe where gravity is dynamical and then it just stops. And then in the region where gravity is dynamical, diffeomorphism invariance is spontaneously broken and the graviton has a mass. So these universes are not like our universe where you have long-range gravity. These universes where the computations of the page curve are performed.
Okay.
Okay.
The next question from the Park White, please.
Yeah, hi, Suvrat.
Hi.
So my question is, the thing is that Hashimoto has written a paper 2 years back, I think, talking about islands in asymptotically flat short-shell black hole spacetimes, right? And so there is no ADS spacetime there, and we are just talking about short-shell spacetime, but they argue that the island is still present. So
I don't think there's any precise computation of an island in asymptotically flat spacetime. What one can, if one looks for minimal surfaces, or one assumes that there's some island rule that holds and one tries to solve for minimal surfaces, one can find minimal surfaces, but it is far from clear what those minimal surfaces mean. And if you really looked at an asymptotic short-shell black hole and one believed the island in the sense that there was an entanglement wedge, like we usually think, that would just be manifestly inconsistent with the Gauss law. So I think the precise statement is that what has been found are minimal surfaces, which one can find in many geometries, but those minimal surfaces I don't think have an interpretation in terms of the entropy or an entanglement wedge.
Okay, thanks.
Okay. The next question from Igor Valovich. Igor, please.
Thank you for the beautiful talk. I have two questions. First, let me comment about the paper by Hashimoto and collaborators. With Irina, we found that there is an important term which was not enough analyzed in the paper. And actually, they did not get the page curve. My question is the following, again about the quantum field theory. Consider the simplest example, free scalar field in the Fock space and 2-point correlators, 2-point Weightman function. Then take psi1 equal to the vacuum. So in the right-hand side, we have 0. That you have to find a vector psi in Fock space such that its 2.5 Weightman function is 0.
It's not 0. Why do you say it's 0? Sorry, the Weightman function in vacuum is not 0. It's 1 over x1 minus x2 squared. It's a Bessel function. Why do you say it's 0? In the vacuum, the Weightman function, the 2-point function is not 0.
But in the right-hand side, you have 1-point correlator.
No, so let me maybe I'll share a whiteboard since this is so I should emphasize that everything I'm saying about the split property is oops, sorry. Yeah. Let me see if I can. Oh, I cannot annotate. I have to share from the iPad. Let me see if I can do that. Yeah. So the split property is the statement that given psi1, psi2, okay, we can find psi we find psi which has the property that psi of phi of x1 xn inside R outside R So this is the split property. So let's say I tell you that psi1 is the vacuum. So I find some state that looks like the vacuum in psi1. In that, for an arbitrary set of correlators, it looks like the vacuum, and I can make it look like whatever else outside. So that is perfectly fine. Maybe the simplest way to think about this is to think of. I'm starting to regret that I put the equation. Is to just think of a product state. If you think of a product state, we just look at a product state of R. So let's say the Hilbert space was HR. The Hilbert space doesn't factorize exactly, but imagine that it did, right? Then it's clear that I can specify correlators independently in the region R and in the region R bar, right? You give me any state, I can always find a state which looks like some state in R and some other state in R bar. I just take the partial trace. And you give me any state like rho 1, even a mixed state, rho 2, and I will write down rho as trace of R bar rho 1 times trace of R rho 2.
Excuse me, it is difficult to follow too many arguments. Let us take only 2-point function.
Okay. Go on, please. Yes. What is with the 2-point function? What is the objection? Hello. So I was not clear what the problem is. With the 2-point function, we take a 2-point function in the vacuum, like both points are inside the vacuum?
No, in the right-hand side, if psi1 equal to vacuum, you get 0.
If you put psi1 equal to vacuum, this is not 0 for the vacuum, right? These are just vacuum correlators. So let's take psi1 equal to vacuum.
Okay.
So now these are vacuum correlators. Now these are not 0. These are some Green's function in the vacuum. If you have only 1 point inside, then indeed they're 0. If you have 2 points, this statement holds for arbitrary insertions. So you can put as many insertions as you like. So some Whiteman correlators vanish, odd number of insertions vanish, but even numbers do not vanish.
So do you say that the right-hand side is never 0?
No, it is sometimes 0. If you put an odd number of, if n is odd, it is 0 if for a free theory.
Okay, thank you.
Okay. Is there any other question, or I should stop sharing?
There is a question from Guy.
Yeah, can I go ahead?
Yes, please. Yeah.
Thanks for the great talk. It was very, very good. I'm still a bit naive about those arguments that you were providing, so maybe my question is a bit silly, but it seemed to me that your argumentation actually rely on the fact that the Hilbert space was infinite dimensional, locally speaking. And I wonder, if we forget about that and actually postulated that whatever quantum gravity theory should have a locally finite dimensional Hilbert space, would you still actually have this breakdown, this property?
Yeah, thank you. That's a good question, actually, and that's so. One could ask this question that's a great question. If one looks at asymptotically flat space and ADS, where I gave these arguments, then one does assume that the degrees of freedom at null infinity are infinity. That there's a continuous degree of freedom at null infinity. So you're right that this uses at some point this uses the fact that there's infinite entanglement in the vacuum, and similarly, this is also what we would assume in ADS, that there's a continuous time variable. So and so you're right, and that's one reason why one might want to be more careful about how one phrases this in de Sitter. And indeed, it's true that if you said there was a fundamental lattice, like there was really a lattice which extended all the way at infinity, like null infinity itself was a lattice, then we would not be able to make this argument. So if you really said null infinity was a lattice, we would not be able to make this argument. And this does assume that null infinity is not a lattice, and that you can obtain all states in the bulk by means of asymptotic quantization. So you're right. We assume there's a continuous structure which is assumed at null infinity and at the asymptotic boundary of ADS. I think those are reasonable assumptions, but you're right. If you didn't have them, then we would not be able to make the argument.
Okay, yeah, I mentioned that because maybe you're familiar with the work by Sean Carroll and others about emergent spacetime, and there they have strong arguments where they would say that locally the Hilbert space should always be finite dimensional as opposed to infinite dimensional, And so they go all the way to say that whatever quantum gravity is, it cannot be a QFT actually.
Yeah, but remember, this is at asymptotic infinity. So there's a lot of volume at asymptotic infinity. So, these arguments are being made at really very far out. So one is assuming that there's a continuum description which holds at asymptotic infinity. But you're right that we are assuming that the language of quantum field theory holds and is exact at asymptotic infinity. Not in the bulk. In the bulk, the metric might fluctuate. But there's a good language one can use for quantum fields. But, this is also how things do work in ADS CFT, in that on the boundary in the CFT, there is a continuous Hilbert space. So in this, the CFT is a local theory which does have a continuous Hilbert space. So that's one case where we know from other arguments that this should work.
Okay, thank you.
Yeah.
Oh, more questions, please. Yes, more questions, please. I don't see any more questions. I guess people are very tired now. Okay.
Maybe a quick question to Suvrat. May I ask?
Do you want to
So in your this asymptotic flat analysis, the diagram that you showed, so the informations were stored near I naught, I suppose, right? So can it be also set near the I plus because that is the future of horizon? Usually the Hawking-Perry-Strominger argument probably says that it is the information will be stored near the I plus rather than I naught, if I am wrong.
The information was stored near the past boundary of Scri plus, so not I plus, but the past boundary of Scri plus. And so indeed for massive particles, we had a proposal that looked at, so it was a union of a subset of the blow up of I naught and the past boundary of Scri plus. Now you could ask, is there some sense in which one can get information on I plus by
near the
So, time like infinity, in any case, one can describe massive particles. That doesn't require holography. Even in the absence of holography, all massive particles end up at I plus. So if you give me data on Scri plus and I plus, even in quantum field theory, that has all data. The surprising aspect of the theory is that information is available on a subset of Scri plus and I naught, which is like the boundary of the Cauchy slice. That doesn't mean information is not available elsewhere. You can also get information at I plus and union Scri plus. So there's a redundancy in how information is available in gravity. And the surprising aspect is that it's available near the boundary of the Cauchy slice, which is I naught and and Scri plus minus. I plus is not in any sense the boundary of the Cauchy slice.
No. By I plus, I meant that, the future boundary of H plus, basically, near about the future boundary of H plus.
Right. So that's not right. So that's not, you're right. So that's future time like infinity, right?
Yeah. No, if I take a Cauchy slice and impose the conservation of charges, then probably near the null, when the null infinity reaches towards I plus, at that point will also be important. What do you think for massless particles?
That point is kind of trivial. You see, it's important that once again I emphasize that in a theory of in a quantum theory, the black hole does not survive forever. So in the end, you have asymptotically flat space, right? You start from asymptotically flat space, you end up back at asymptotically flat space. The black hole does not live forever. Right? So in a theory of quantum gravity, the notion of edge of the horizon as a part of the Cauchy slice that you're speaking of, that's a very classical notion. Right? Quantum mechanically, the future boundary is Scri plus. So I plus is an interesting, so if you don't have massive matter, then I plus is just trivial, right? If you do have massive matter, and I plus is the part where all massive particles end up, it would be a natural place where all information about massive particles is available. So that's certainly an important place. If you can extract all information about massive particles from I plus, and then you can combine that with information about massless particles. And that certainly we could do. But I plus is not in any sense the boundary of the Cauchy slice. It's where even in quantum field theory, all massive particles end up. The unusual fact about gravity is that things are also available near I naught and Scri plus and Scri plus minus.
Okay.
Okay.
Thank you.
More questions, please? If there is no more questions,
Oh, I have one more question. Sorry.
Okay, please.
Thank you again for the very clear talk. As I understand, some authors who write about the islands stress that their computations are acceptable only for eternal black holes, not for evaporating black holes. Do you agree with this?
Indeed, the precise computations have been done for eternal black holes, but even there, these are not eternal black holes. They're in the presence of a non-gravitational bath. So they are not eternal black holes in a standard theory of gravity, where again islands would be inconsistent because of what I said. They are eternal black holes in a theory where the graviton is massive and gravity stops at some point. So it stops and then becomes non-gravitational. So by hand, there's an EDS boundary and a non-gravitational bath. The eternal aspect is important, but it is believed that with more technical work, one could do it for an evaporating black hole. But the non-gravitational bath is not a technical obstruction. It's fundamental to the whole program. There's a non-gravitational bath, and that forces the graviton in the region where it is dynamical to be massive in all dimensions larger than 2. And that's the reason I think it's not a good model for a realistic theory of gravity, not just because the black holes are eternal, but because of the non-gravitational bath and the massive graviton.
Thank you very much.
Thank you.
Okay. More questions? If not, let's thank Suvrat once again. Thank you very much. We have a lot of discussion.